Oh, hi. Oh, sweet. Okay. And, yeah.
There's a similar product.
Hey, good evening, everyone.
Europe. It's really cool.
Good evening, everyone.
Good evening.
There we go. That's how we
Robbie.
go. That's how we get started. My name is Robbie Mickelson. I'm one of the organizers for Climate Link. You may have joined the meetup, what it used to be called CleanWeb. So we've gone through a rebrand and an upscaling of the mission entirely. So Climate Link is both a meetup and an online platform that's in works. And our mission is to facilitate the deployment of $1 trillion per year for climate action and sustainability between 2020 and 2050. It's a little bit aggressive, but we can get the slow clap going if you want.
No, it's about to jump out of my chair.
Okay. So if you read the IPCC report last month, they said we need to spend way more money than we have been, and we need to do it faster. So this 1.6 to 3.8 trillion dollars per year is only on supply side energy. It doesn't go into ag, food, demand side, all sorts of other things. So in total, some numbers I've seen are somewhere between $4 and $10 trillion globally per year between 2016 and 2050. So we need to go back in time and spend more money to not go above 1.5 degrees C temperature.
Encouraging.
Yes. So I called Dr. Who. We're working on this. But really, so before on CleanWeb, we were focused on early stage clean tech companies. And as I started talking to later stage companies, banks, not-for-profits, everybody has the same problem. And at every stage of development, it's who do we connect with to move our product forward? Whether it's testing and validation, it's manufacturing, it's finding the right customers to move things forward, it's getting the capital. So Climate Link is building the links between all of the network nodes. And so whether it's a chemistry company, a software firm, not-for-profit, for-profit, government agency, our mission is to remove the discovery phase between all of these different network nodes so that they can focus on the next two phases of diligence and deployment so that we can reach the scale in the time required to not blow up the planet. So we've got the online network that's in development. We've got these physical meetups to showcase the technology and develop the local ecosystem. And hopefully that will be a positive feedback loop and help grow the network and move things forward. So this is tonight. Are all of you members of the Climate Link meetup group? Yes, yes, yes. Okay, good. So that's that. Here's a bunch of partners, really fancy logos. Next month, we're covering SB 100, California's path to decarbonization of the electricity grid. And we've got the CEC Commissioner, David Hochschild, will be speaking. And right now, we're slated to be at Orange, Silicon Valley. Also got Pete from PG&E, our amazing host here. Maybe we'll move over here instead. So with that segue, I want to introduce Pete Shoemaker, our host for tonight from PG&E, who moves to host. He's our host, so he'll tell you about. Oh wait, one more thing. So part of climate change is the warming weather, drying out of forests, leads to more forest fires, and that's why the air quality is so bad. So if you don't know, I just left the meeting with someone from the EPA, and basically, if you don't have one of these and are wearing one of these on the street, I highly recommend it, because even though it doesn't hurt when you breathe right now, you are doing damage to your lungs with the amount of particulate matter that's out there. So I highly recommend, don't get one of those little medical masks, which is just for covering your spit. Get one that's an N95 mask or N99, and that will actually protect you. So thank you, stay safe, and here's Pete.
Where do you get those? Sold out.
Amazon, Home Depot. I got this in Delaware the other day, so you've got that outside the bay.
Okay, I just want to make a brief comment about plug this place. This is a PG&E training center. I think
Anybody, a lot of you first timers here, and that's nice to bring you in here. This is a training center funded by a small surcharge of everybody's PG&E bill. So it's essentially funded by the ratepayers and it's all free. We have a wide variety of classes that include the class I just had today, which was on PG&E rates and tariffs. I have a lot of the IDSM, which is a lot of this grid integration stuff, integrated demand side management, we call it, solar, batteries, demand response, microgrids, all that sort of thing. We have a whole building commissioning tools, the lighting classes going on over here. It's a great place to educate yourself or for people in your company who may be hired for a niche in your energy company and then want to broaden their horizons for free, good networking. We also have a very, very large tool library manned by experts that can give you blower doors and sun eyes and bloggers and all kinds of stuff for free. So it's a really good resource to learn and network here, so please come back. And our schedule is on, you can take cards, and Bradley will have, you have the email list of the folks here. I'll send you out sort of a link to PG&E schedule, this schedule here, and plug this. So that's it. Please eat the food, because, you know, that's what it's there for, and I hope you come back. So much.
Thank you, Pete. So now we've got Brock Petersen and Casey Heier of SmartWires, blanking on the name all the time. So they're going to talk about their technologies. Yeah, all I know is that it can reroute electricity on transmission lines, go from congested to open, and I've now exhausted my knowledge of their company. So I'll let you two take it from here.
We'll talk about it for the next hour, so you'll have plenty. One, just say, thanks for having us here. We're super excited to come talk, speak. One, definitely shout out to the PG&E Energy Center. I've come here for a couple of events and they've been awesome, so definitely take advantage of those. Also, I definitely wish I had one of those masks. I made a really bad choice of playing soccer last weekend in LA at a tournament, and I still can't take a deep breath, so definitely wear the mask. So to give it, I guess, a quick intro on us, I'm Brock Petersen. I'm a product development manager at SmartWires. I lead a global team of probably about 50 engineers who are developing one of our two products that we're developing right now. And then Casey.
There's another mic there, right up front.
Oh, boom.
Push it up.
Hold it down for 2 seconds.
Hello?
There you go.
Great. I'm Casey Heier. I'm our Director of Mobile Solutions at SmartWires. So we're going to get more into that, but basically it's our newest deployment method for deploying the devices Brock and the team are developing. So I kind of head up some of the product development and business development. And yeah, thanks for having us here, Robbie. And Brock, you want to go ahead?
Yep. Casey and I also we had the good fortune of we both did the same master's degree program together, so it's fun to get up here and chat because we don't get to work together too often. So it was fun for us putting this together. We want to. So I think actually to start things off, we really want to make this as interactive as possible. What you'll see is a lot of the concepts we're going to go through aren't, it's not your storage, your solar, the things that you're used to seeing. So one, we're very open to questions. We want to make this interactive. It is kind of a good way to start off. We'd like to just raise your hand. What are some of the reasons of why you signed up to come see this talk, or what are some of the things that you're interested in hearing about today? And that can kind of help dictate a little bit of how we go. So yeah, yes.
I guess the challenges that utilities are facing and how their business models might change into the future.
Excellent. Yes.
Hi, my name is Ali. I'm with Terra Verde. We're working with CCAs to help them figure out how to deploy DERs to the grid by working with the customers. And I thought the topic was very relevant.
Excellent.
Give me 1 second so I can just write these down.
How it will enable DER, is that kind of?
Yeah, for CCAs to promote it to the customers. Yeah.
Okay. /CCA. Awesome.
How much communications you need to operate the graph?
Gotcha.
And then how you achieve the impedance changes, but still maintain efficient transmission of current.
Impedance with efficiency. Awesome. Any others?
Yeah, I was looking at it from the standpoint of communications and control systems between distribution and transmission. So as solar and microgrid project development from commercial and residential, this is two different worlds down at the distribution end versus you guys' end. But clearly they're going to have some interplay through CL-ISO, otherwise I'd like to understand those rules.
Yep, awesome. Yeah.
Can this technology help improve the resiliency of the grid itself in terms of either natural disaster or terrorism?
Excellent. This is a good list. All right, we'll do one more, then we'll kind of jump into it.
Figuring out if there is a way to reduce transmission upgrade costs for utility scale solar assets.
Awesome. Yeah, I think most of these we'll touch on, and we can definitely try to emphasize some of them. Does anyone else have a burning one? Going once, going twice? All right. Awesome. So what we'll do is I'll first kind of give you a quick overview of SmartWires, and then you all are lucky. I actually gave a TED-style talk last week to Stanford professionals in energy, so I'm going to kind of go into some of that talk, which will give you a good highlight of why this is a problem, the problem that's facing utilities and how we can solve a lot of those challenges. So SmartWires, we actually, I know I saw on the Climate Link slide, RPE up there. So we received a RPE grant about 7 years ago to try to commercialize some really cool technology out of Georgia Tech, and have done a great job of doing that, and are really one of the darlings of the RPE program. We've been around for about 7 years. We've also done a deployment with PG&E, and as you can see, we've done a deployment with a lot of utilities around mainly North America, Australia, and Europe. We can kind of, if we want to go to a little bit of the nuances of these different markets, we can also do that in a little bit. Now we're developing power flow control technology for the transmission grid, but we'll kind of get into some of those futuristic applications and where we really see the market going, where we want to go as a company. The changing grid. So really, if you look at it from the legacy standpoint, SmartWires is really kind of hitting the market at the right time. And the legacy standpoint, you had dispatchable generation that we could control, one-way, well understood power flow. It was relatively easy to site new lines, and you understood your future load growth. I mean, new factories take years to come online. That's not something that's happening in a matter of months. You fast forward that to the energy system of today, where we have intermittent renewables, two-way power flow, lines, NIMBYism, no one wants lines in their backyard, and then the future load growth. I mean, we all seen those graphs of how every year, it's further and further off from what we're actually seeing. In the new energy reality of today, I mean, you can put a 100 megawatt data center, and that can come online in 6 months. So being able to handle that from a utilities perspective is not an easy challenge, and is really different from the way that they operated 10 years ago. One of the things to highlight, though, hopefully you notice what did not change from the legacy energy system to the energy system of today, is the grid. Really with grid, Smart Grid 1.0, a lot of that was just monitoring. It was smart meters, it was being able to turn a customer off who hasn't paid his bill, it was being able to get your green button data, but there's no real-time control or anything like that. We really need this to happen if we want to start solving some of the utilities grids that they're seeing from this new reality. To highlight some of those problems, whenever I jump on CL-ISO, I think I took this about a month ago, but really you could get on there about any day and see issues like this, where when you click on the little dots, I mean, they'll tell you exactly what the LMP is, and they'll tell you exactly what the breakdown of that LMP is. And you'll regularly see almost a $1,000 increase just from congestion costs. We'll get a little bit more into congestion and what that is.
Can you define LNP for
Oh yeah. Locational marginal price. So it is, there are nodes on the grid where the utility will price electricity at that node because of the generation assets that you can get there and what that costs from the generation asset standpoint. We're also, okay, so this is an economic standpoint, is the way that the utility looks at this issue is an economic issue. There's also adequacy issues. For curtailment, this is a really interesting to me as I was kind of researching this, almost 40% of the hours in 2017 in California, we curtailed our wind and solar. And this, as you can see, is accelerating quickly. And we're actually seeing this as a real impact on the ROI of new renewable projects on the grid. So this is something that's not just hurting us as ratepayers, but also is hurting the people who are building these renewable generation plants. We're also seeing congestion-caused outages. So this is the reliability side and safety side of the house from the way that the utility would look at it. So this was in July of this year. Some of the wildfires at the time in Northern California caused transmission lines to go offline, which exacerbated congestion. And what that resulted in is actually in Orange County, 10,000 customers had to be shed. That load had to be shed to keep the grid up. And that was all directly attributed to the wildfires in Northern California. So I kind of, as I was going through that, said, this is the way the utility looks at it. So trying to get us a little bit in the utility's frame of mind, as they're looking at their grid and how they're building it out, they're mainly looking at they're looking at three considerations. So they'll do 3-year plans, 4-year plans, 5-year plans, etc. And they'll look from an adequacy and safety standpoint, so that's just ensuring that the lights are on. They'll look from an economic standpoint, so where can they put in assets to alleviate congestion of having to run more expensive generation. Then also looking at their grid of what is due for replacement, so that construction and maintenance. So what causes congestion? Congestion is caused because electricity, the electron's always going to flow down the easiest path. However, when we build transmission lines, we rate them for a certain capacity. So the electron doesn't realize that a line is reaching its capacity. It's just going to keep flowing down the easiest path. And on the transmission side of the house, we always have parallel paths. So if one line goes down, the grid can't go down. So there's always multiple transmission lines that will carry power from places like Hetch Hetchy, or other generation plants here, or Moss Landing, to load centers like San Francisco. So if one line comes down, you can still get that power from the generation to San Francisco. So in this pretty simplified example, you'll see that one of the lines is reaching its capacity limit, while the other lines still have excess capacity. And this is something that is seen very regularly on the grid. And when this happens, the utility has to make a couple decisions in real time. They can curtail and run the grid less economically. So when we saw that chart of all the LMPs and the difference in cost, that's because in this area I'm able to get the least cost generation. However, in this area, the grid over here, don't have enough transmission capacity, or it's being congested to be able to get the least cost generator. So I start running a higher cost generator, and then I turn off or curtail those other generators. In the long term, what the utility does is they do those transmission planning studies, and they can build new lines, which is becoming more and more difficult and also very expensive. They can reconductor a line, which in this example, I think that my auto progression of the slides is still on from the 15 seconds, which is why it keeps wanting to jump. But we can reconductor lines, which is just build a fatter line. So if I need to get more transmission capacity through, I can put up a bigger line. Or there are some fixed custom built solutions to route power. So if I have a known issue that I know is going to be there for the next 20 years, there are solutions that I can go to where they will be custom designed and built in the span of about a couple years for that need. But again, that need has to be a couple years out, and that need has to be well defined, and a need I know is going to be there for a long time to deploy one of those other assets. What we at SmartWires are doing is really taking what Waze has done from the road side and trying to apply that to the transmission side. So Waze in real time understands congestion on roadways and reroutes vehicles in real time to alleviate that congestion. So when I jump on Google Maps to drive here today, the shortest route to get here was not the route that was the quickest, right? It said go this other way. So same concept of what we're doing as we apply that to the grid is how can we dynamically dispatch transmission lines? So as we know from Physics 101, electricity is going to flow down the easiest path. Well, why don't we dynamically change what that easiest path is? And that is what we're trying to do at SmartWires, is create dispatchable transmission lines that the utility in real time can route electricity. Because as you have solar coming on in the day and then coming off, and wind coming up and down, your power flow is constantly changing. So being able to do this dynamically and being able to do it in a range set really helps with the utility's problems. And to kind of highlight this as a real life example, earlier this year in MISO, the Southwest Power Pool, as the LMP was diverging, so as you can see that the cost at those different locations was increasing, and wind was actually being curtailed pretty drastically. They used power flow control techniques in real time to homogenize the LMP and be able to get more of that wind out on the transmission lines. And that's all from the fact that we have plenty of transmission capacity, we just don't have a way to dynamically control how it's used. To put that into a very high conceptual, and I know someone asked, how do we actually change the impedance on the line? We'll get to that detail in a second, but to give it from a higher level view of, essentially if you think of the grid as a large pool of water, that water is going to flow down the hoses, and say one of those hoses starts reaching its capacity, I can squeeze that hose and push water away and down other hoses that have excess capacity. Alternatively, I can make one of those hoses bigger and pull water to me away from another hose that's reaching its capacity line. So that's literally what we're developing technology to do to the grid, is to change the impedance on the grid and make it easier or more difficult for electricity to flow down lines, as we understand in real time where that congestion is happening. That's to get more throughput with the existing infrastructure. So from a product standpoint, what we received the RPE grant for was these magnetics-based technologies with the Power Guardian, the Power Line Guard is actually what the technology was at the time. So these are the early technologies that we developed that would just increase the impedance of the line, so make electricity not want to flow in that direction. What we have developed later, and we're about to install the kind of version 2 of it on a customer's lines, is a smart valve. And that can act like an inductor and push power away, can also act like a capacitor and pull power to it. So in this example, instead of pushing power away from the congested line, we can pull power to a line that has excess capacity. So is that, from a high level, does that make sense? Any questions so far? Yes?
So you have to be on the AC network. You can't do it at DC interconnection. You'd have to have like some.
Yes, so that's a...
Brock, can you repeat the question?
Oh yeah, so the question was, do we have to be on an AC line, or could we do this on a DC line? That's an excellent question, someone who definitely understands how electricity flows. The answer is yes. This is only applicable for AC lines, this type of technology. DC does not have an impedance, it just has real resistance on it.
But I was asking that because of the SEAM, like, the National Energy Labs SEAM study where you have to interconnect between East and West.
Yeah.
And, like, those might be points, but you could do something with a special AC network you could have multiple DC connection points in stereo.
Gotcha. I'm not familiar with that study, or...
I just know that seams often have the DC links between.
Yeah, it's just how you can interconnect the networks but not leave them coupled and susceptible to failure.
Yes.
So I don't mean to take you off your...
No, so, or I'll repeat that same for the crowd. Notice the question, or the statement was around, how could this work with seams? So basically, if you look at the different regions in Europe, or let's say the US, right? So ERCOT, Texas, essentially is its own grid and has its own frequency that is not linked to the other grids in the US. But they still want to be able to share power back and forth. So they'll have an interconnection. That interconnection will go to DC and then back to AC, so that the power that you're transferring, let's say, into Texas, will then go to DC and then become transformed into AC that's on the the same frequency as the ERCOT grid, or if it's going out, you have to change it to make sure that you're not injecting injecting real power that is not synchronized with that grid. So those seams they use power electronics in a similar way that we do, but it's not necessarily a power flow technology. Great questions so far. I will say that DC gets spoken about more these days. However, I think we only have a couple of DC lines currently in the U.S. So if you look at it from a percentage-wise, I mean, most all infrastructure is AC. This is just kind of, I don't know, it was part of the Tech Talk too, to put some big numbers up there. But if you look at it, we spend about $90 billion a year on transmission upgrades. We think technology like ours could easily address 15 billion of that just from a capital standpoint. Congestion costs, the latest number I've been able to get is 2008, which is about 8 billion, but I know it's more than doubled since then. So that's also a big number of kind of economic benefit that we could provide. And also outages, in case we'll go into a little bit more of what we can do with outages. But if you'll notice in that photo, we have a laser pointer, yeah, so I mean that's, New York should be there, a lot of, other New England areas. So that was a big outage in the U.S. We do about, or no, excuse me, I can't remember if that number is U.S. or globally, but about 150 billion annually in outages. So that's also something where we can't necessarily prevent every outage, but we can definitely help prevent some and help get the grid back online quicker. So SmartWires technology, like you said, we received an RPE grant. We developed that Powerline Guardian. I will mainly be talking about the new technology, which my team's been focused on developing that technology, which we're going to be deploying in Central Hudson. It was supposed to be beginning or end of this year. They had to send some crews down for some hurricane help, so we're going to be doing it beginning of next year. And then you also see the mobile, which is what Casey's working on. I won't go through the rest of these technologies because they've already kind of all built up to the current technology. As we said, some are just pushed, and the smart valve is push-pull. We'll go to depth there, but we'll kind of stop here. So the smart valve, this is what allows us to increase or decrease the impedance on the line. Is anyone an electrical engineer here? Sure, we got a couple. Okay. How many engineers do we have here? A few more. Okay. Has everyone taken physics before? Yeah, physics. All right. We'll be in the boat. So we're developing this technology. It's we call it 1000, 2000. That's its MVA rating. So the Smart Valve 1000 will produce about 1,000, or will produce 1,000 millivolt, 1,000 volt amps, and then the Smart Valve, or excuse me, kilovolt amps. 2000 will do 2,000 kilovolt amps. And that is sort of the 2000, I mean, that's the equivalent of about 5 Tesla Model S's, to put that in perspective. So in that little box, we have the same powertrain, essentially as what an electric car would be, and that would be about 5 Tesla powertrains in that box, and that's what we're deploying on the grid to increase or decrease the impedance on the line. The way the box works, and I'm kind of going a little bit of depth here, and if we have more questions or want me to go more in depth later, I'm happy to do that. But it's essentially set up just like a big inverter. We've just adapted that technology for this so that we're injecting a voltage waveform in quadrature with the current waveform on the grid. And by doing that, we can slightly offset our voltage waveform leading or lagging. And by injecting that additional, pretty much ohmic resistance, we can simulate what a capacitor would do and inject capacitive load, or what an inductor would do and inject inductive load. And what that does is when we go inductive, we're going to push power away and make it harder for electrons to flow that way. And when we go capacitive, electrons will want to come to that line. So this is a really cool technology. However, living on the transmission line, and these are in series on the transmission line. Maybe I think, oh yeah, I'll go into a little more here. This gives you the one-line diagram for the electrical engineers in the room. But we're in series on the line. So if you think about a voltage, we're on high voltage AC transmission lines. But because our product is in series with it, we don't really see a lot of voltage on our product. So that's one of the kind of advantages that we get to take, is that our product is, essentially is floating at line voltage. So whatever voltage drop is across our product is all the voltage we'll see. And that voltage drop is how we inject, because we're injecting voltage on the line. So we do see a little bit, but it's really is low to medium voltage. However, we see a lot of current in our devices. So nominal line current could be 2,000 amps, nominal line current could be 4,000 amps. And our devices have to be rated to handle that. But what is very difficult to handle on a transmission line is what happens when a fault comes. So when a fault comes, you go from those 2,000 to 4,000 amps to where you could go to, what our product is rated for is 170,000 amp peak, about 60,000 amps RMS. And that device, the smart valve I showed, that's what's doing the power flow control, acting like an inductor or capacitor. However, so the smart bypass is the device that protects the smart valve. So when that fault current comes, a lot of our engineering work and IP has been around how do we handle that current when 170,000 amps are coming at our little power, semiconductors that are essentially what you put in an electric car. So these two devices are kind of go together to be able to provide that package of what SmartWires is providing to the grid. So that's a quick overview of the products and exactly what we're actually selling utilities. Yes?
Sorry I didn't get the technical diagram before, but my question is it one valve per line, or is it one per
Got one valve per line. Okay, yeah, great question. So one of the ways that, that's kind of skipped over this, one of the ways that we've developed this technology is, it's like a Lego block. So say we do a grid study and it shows, PG&E on their line, needs, 4, MVA of power flow control. Well, we could sell them that today, and then say in a year from now, so that would be, say 3 devices, so like 1 per line is what you might need. Then let's say, a couple years from now you all of a sudden need 10 devices per line, so 30 devices. So you can add that on just like you would add Lego blocks, and that's one of the ways that we've made it scalable so that a utility can take advantage of buying something today and then still have the ability to use it tomorrow and add to it if needed. So where they're not just stuck building a new transmission line or doing something that they're going to have to pay for the next 50 years on the grid. We've also made it to where they're modular, so where you can take them down and actually install them somewhere else. Kind of Casey will go into obviously a lot more of that. Good question. So you need to keep it symmetrical with your phases, but how many we deploy on one phase, it's up to the situation. Any other questions now? Okay, so I'll kick it off to Casey, where he'll go into a little bit more of what we're actually doing, one with mobile, and then some kind of case studies and how we're actually implementing this with utilities.
Yeah, thanks, Brock. And we can take a bunch of questions at the end and dig as deep into the technology as you want to get. But I think, so just to kind of step back and step up a level, I think we're all here because we all care about climate change and the burning need to figure out solutions to address it. And for me personally, I've always looked at the power system as a key part of this. Obviously, there's a lot of carbon-intensive energy sources and generators on the grid. And if you look at the challenge at the 50,000 foot level, we've got to find a way to swap out these old dirty generators and install a bunch of renewables and clean power across the grid. And I think what's often overlooked is that we have this massive network of wires, steel in the ground, copper in the air, that has been built up for over 100 years, and that it doesn't really get talked about. I think we tend to think, oh, everyone's going to go off grid and have solar and storage at their home, and it's going to be great. But there's a huge question of what do we do with all those wires in between, and I think SmartWires really tries to address and make the best use of these investments we've made over the last 100 years to build a reliable, efficient grid that we still all depend on. And as Brock has mentioned, the way utilities plan and invest and build and operate the grid has changed a lot in the last 20 years in particular. There's a lot more uncertainty, there's a lot more variability, and there's a lot more of a need for very flexible and responsive grids. And our technology can help enable utilities to have that type of feature on their systems. And Our devices are all modular, they're all rapidly deployable, they're all redeployable. You can have them at one location and on a 230 kV line and move it down to a 69 kV line over here, and there's no custom engineering that needs to go into the device itself, which is kind of what makes it unique from your traditional legacy solutions. And really this whole mobile concept that I'm about to get into is sort of the fullest realization of the most unique aspects of our technology, right? The rapid deployability, the redeployability, the scalability, and really all we've done is find a way to basically have our devices ready to go inside a trailer, a container, and wheeled up to a site and installed in less than 8 hours. And I'm about to go into some of that there, but I just kind of wanted to set the stage a little bit there. So just going back to Brock's earlier example where we have this very simplified planning scenario that's predicting the future overload. We've got to reduce the power flowing on that line, and as Brock said, we can curtail it, we can curtail generation or shed load, and then the long-term fixes are obviously to build a new line, put in a legacy fixed solution like a phase shifting transformer or something large there, or we can do a reconductor. And a reconductor, for those of you who don't know, is just essentially taking down the old skinny wire that's up there and replacing it with a bigger, fatter wire that has more capacity. And this is probably the most common approach utilities take. So let's assume, so first off, you can use our technology to resolve that overload. You can do what Brock was saying and increase the impedance of that overloaded line and push power away. You can also,
Question on the 99%.
Yeah.
So is that set sort of the physical limit of the line, or is the utility set, okay, this is 100% capacity for this line to reach a certain longevity of the line economically?
Yeah, so the limits are usually set based on the materials of the conductor itself. So if you have too much current flowing on the line, it's going to heat up, it's going to expand, it's going to droop, and eventually if you run it hot enough, it's going to melt. And so if you've seen some of the things in the news about PG&E potentially being responsible for wildfires, sometimes if they're running their lines too hot and it's dragging down into the vegetation, that's kind of what happens. And so that capacity will be dictated by the type of material.
Yeah.
Good question. Yeah.
Is the 50 megawatt number up there calculated by is there any other numbers that can help us get to that number on the slide, or is how do we get?
This is kind of a very oversimplified, generic example, but I think we have a couple of case studies that are a little bit more detailed.
Okay.
Yeah,
that'll add up.
I say one thing too. Someone here is not from this team here, so I'll kind of take this like the 2-second pitch. But we have this awesome solutioning team that actually works with utilities to study their grid and say where should we deploy these, and they're actually trying to develop automated ways to look at utilities grids and say, hey, for here, you should do SmartWires. Maybe here, reconductor makes sense. Maybe here something else. But that's something that we're also looking at is how can we automate the transmission planning process, and that's really what gets to these numbers is that team can provide those numbers with their studies.
Mm-hmm.
Yep. Thanks, Mark. So let's just jump ahead and say the utility doesn't want to use SmartWires to resolve that overload. Say they need to reconductor that line. And they could need to reconductor the line not necessarily because of even an overload. It could be the line is just simply too old. It's not uncommon. PG&E has lines that are 60, 70, even 80 years old on their system. So eventually, structurally, they just want to replace them. And the challenge is, when is the utility able to do that work, right? If you take this line out of service to rebuild it, reconductor it, whatever you're going to do, that power that was flowing on that line has to go somewhere else. And so the utility is often limited as to when they can do that. And just to illustrate this a bit more, this is an example we took from one of our Australian customers. And what it's showing is basically the system demand level for a certain portion of the grid throughout the year. And it's in Australia, so you have a summer peak in January or February, but this same basic shape is pretty common across all grids around the world. You kind of have your summer months where everyone's running their AC, where energy demand is high as your peak time, and then you have a smaller peak in the winter, and then in the fall and spring you have the lowest level of demand. And that's typically when utilities would be doing a lot of this construction work. And so in this example we looked at here, the typical construction season was about 16 weeks per year, 10 and 6 weeks. And so if you're looking at reconductoring a line, say a really long 50-mile line, it wouldn't be uncommon for it to take, say, 45 weeks to complete. Now you can imagine if you wanted to get that done, it's going to take you a few years, 3 years roughly, to get all that work done. And so utilities are under more and more pressure to get all this work done to accommodate all these changes in generation and everything happening on the grid. And the windows are actually shrinking. There's less certainty in how much time you're going to have to do the construction work. Something could happen and you have a heat wave earlier than you expected, and suddenly your system demand goes way up and you've got to stop work on all your lines. So this is kind of a very common type scenario and challenge that utilities are dealing with. So if we jump back,
the reason why they're stopping work on that line is a lot of times they have to re-energize that line to be able to get the capacity to serve that load. So that's why they're saying we stop work, re-energize, like electricity, run on this again, and we'll try to get to this project if we can.
Yeah, thanks, Rob. Jumping back here, so if we're going to target this line, let's assume this is just a summer peak case here. When you take that line out of service, you're going to have problems eventually on the other parallel paths. So you wouldn't be able to work on the line during this period. And the great thing about our mobile solution is it's a rapidly deployable system that has a temporary installation method. And so it could be wheeled to that line just when you want to do the construction work and resolve that overload, pushing it onto the other parallel path, and enable you to take that line out of service for a longer period of time to do the work. So if we jump back to that graph, the new load level that the utility can accommodate to have that line out of service can be much higher now, because you're eliminating that binding constraint that said, hey, you have to put this line back in service. And so you can actually do the whole reconductor project in 1 calendar year instead of 3. And there's obviously huge benefits to that for the utility. They have fewer crew mobilizations and demobilizations, which saves cost. They get this line in service quicker, so you don't have to take as many operational risks to keep your grid up and running. So this is kind of a completely new way of looking at this challenge for utilities. This has never really been done. We've never had dispatchable lines. We haven't been able to temporarily change line impedance like this very quickly. So it kind of opens up this whole new world of how the utility thinks about planning, building, upgrading, and operating their grid. And so this actually was, this whole mobile idea was actually inspired by our customers. We had a lot of our fixed installations, and the grid operators got their hands on the devices. They were turning them on and off. They were seeing the impedance change, and they thought, wow, how valuable would this be during my clearance windows, my construction and maintenance clearance windows, if I could kind of adjust the impedance to widen those windows. And so over the last year and a half or so, I've been working with the team at SmartWires to kind of further vet out there is a real business case here for this type of tool, and then we've started to build our first mobile solution this year. So this is our Gen 1 mobile solution. We used this ISO container as sort of the exterior shell of this. And this can be, this is a widely accepted unit that can be transported by truck all around the world without special permits. You can throw it on a rail car and transport it by train. You can put it on a barge and ship it all around the world for really, really cheap. It can even be lifted by a helicopter winch and flown into remote places where you might need it. And it's all just about having our devices inside the container kind of ready to be able to pop out and be hooked up to the transmission line as quickly as possible. And I can kind of give you a simple cutaway view of what's going on the inside of this. So you have our big power flow control devices there sitting in the transportation mode. There's an insulator stack right here. And basically through a series of different stages in which we use a hydraulic lifting mechanism on the inside, we lift the devices up to the roof level, shove the insulator on it, and push them all the way through the roof over here. So when they're up in this position here, you can route transmission line conductor down through the devices and then back up to the transmission line. I think, yeah, there's kind of a simple diagram here showing this, but basically we have to find a way to get the devices in series with the line. And so we can insert some insulators to break the line here in the original transmission conductor, and then drop jumpers down through our devices and then back up. And so all this can be done in about 8 hours if you have the right kind of site conditions. You know, if you're able to go inside an existing substation and there's room and everything, it's kind of the easiest, fastest way. But we can also deploy these out in the right-of-way in a temporary fashion. So just anywhere where there's an overhead line, you could park this thing underneath it and drop conductor down and have it hooked up pretty quickly as well. Any kind of questions? I'll kind of pause there.
Have you thought about this for storms and things of that nature? I mean, this is 8 hours is fast. You know, you have like large outages that happen, you know, because lines go down and they have to cut power for a week or.
Yeah, and that's one of the newer things we've just started to explore as we got the installation time down. I think originally a year ago we had a goal of 2 weeks. Can we find a way to install this in 2 weeks? And then over the last few months we've been finishing up our first mobile container and running it through its paces and finding ways to improve it. And we very quickly got down to 8 hours, and so we're just starting to think about how can we use this for disaster relief, emergency preparedness, especially given, you know, the wildfires going on here, the hurricanes down south. There's a lot of interest in this, and we're just starting to understand how it could be used. But just to give a quick example, so in a hurricane type scenario, you might have a hurricane come through, it's going to wreck your utility system, you're going to have power outages everywhere, you're going to have to rebuild your lines piece by piece, right? And so there might be an opportunity to install our mobile unit to allow you to turn power on to more customers more quickly, right? So say you have 2 lines that are out. One of them is very quick and easy to fix. Say it's only got 2 towers that are down, and you can fix those and have it up and running, but you can't energize it because as soon as you try and open or you close a switch to run power down it, there's going to be too much power flowing down there until you fix this other part of the system. But if you had our mobile unit on that line, you could kind of control the flow of power in a way that would enable you to flip that light on sooner for a certain portion of your customers while you finish your other work. And we're currently starting to talk to utilities around how can we study their systems and plan for these types of scenarios. But it's a pretty complicated effort. But as Brock mentioned, we have a whole team that's kind of working on different tools to sort of optimize where you want to place these things in the event of something like that happening.
Yeah, I mean, can I give that another example? Because I do think it's super relevant now. You know, how do we do it for wildfires as well? As you know, Casey was saying earlier, we're having energized lines that are drooping into vegetation. You have a dry day, you have Smokey the Bear. It's a red day, don't do a campfire. Like those types of days too. You could look at, all right, PG&Es. Like I only want to run this line at 25%. How can I do that? And that's a similar thing where we can put our devices on that line or other lines to pull power away or to push power away from a line that we don't want to energize so that we can try to prevent fire. So it's a way to not only get us back on quicker, but we could also look at prevention as well.
Yeah.
Just trying to understand so sometimes like lines are like 50 miles, 100 miles long, right? So is just like one of these enough to control flow across the whole line? Or do you need like multiple?
Yeah, so the question was, some lines can be very, very long, 50, 100 miles long. Do you need one of these to control the flow of power or multiple? And I think it's really a case-by-case basis. It all depends on the topology of the network, where you're at, and how much impedance change you actually need to resolve the problem. Sometimes it might only be a very minor overload of 102%. In which case, one of these units would probably suffice. But if you're trying to solve, that's kind of the great thing about our technology is it's, all the devices are effectively the same, so it's very easy to add more in series to meet the need that you have. But I would say, as we've started working with customers, we find 1 or 2 of these mobile containers solves the majority of the outage management type applications we would see. Yeah.
Do you see utilities, primarily vertically integrated municipal, that also sell electricity as well as manage the wires? Do you see interest from them for using this kind of a device for actual congestion relief economics? I mean, I see the value for like hardware, like hardening the grid and safety and replacement costs, like for an investor-owned utility like PG&E would do. I'm curious about the congestion relief side. Are the economics there?
Yeah, they're definitely there. I think I actually might have a case study in here somewhere where we could speak to that. But yeah, if you take even the example of the outage management graph, the graph that I showed you earlier, you know, you may not be limited to those windows, and maybe outside of those windows you can still take that line out of service, but you're going to have to fire up very expensive generation. So we've worked with a couple customers to identify applications where we use mobile to relieve the congestion during that reconductoring construction work. So that's another interesting way to address congestion. We've also done just system-wide congestion studies like Brock showed earlier in the SPP footprint. So it's definitely a use case that we're looking at with utilities. I'd say it's, for a lot of utilities in the US, they tend not to value solving congestion problems as much as reliability problems, because all their energy costs are passed through to the customer. So the incentives in the US aren't quite aligned with prioritizing those types of projects.
Is it about merchant?
Yeah, sure. And something else, so most of our customers to date have been, you know, utilities. They've been your transmission system owners and operators. We've actually looked at working with the generation owners themselves, and wind farm and solar farm developers. And mobile is interesting to them because typically what happens is when they enter in the queue and they're wanting to get connected to the grid, they're often waiting for certain grid upgrades, like reconductoring projects, to be completed before they can be online and delivering full power. And we've identified a few applications where you could use our mobile unit and actually enable them to deliver more of their power sooner and in advance of that reconductoring work being completed. And I actually have a slide on that. I think it might be, this one is kind of similar. Let me just talk through this because it might help answer some of the questions you guys have. So this is an example with a European utility that we're working with. And then this kind of simplified depiction of their grid, what they have is they have about a gigawatt of wind generation that's seeking to connect to their network in a certain part of the grid. And this substation A there on the map is a bottleneck that prevents them from having access to the market. And so there is this full renovation of substation A plan where they're going to upgrade a bunch of buses and other equipment there to eliminate that constraint, but they can't get that done until 2024. And so in the meantime, we studied, well, can we deploy a SmartWires solution near that substation to push power away from it and onto other parallel lines to enable more of that wind to come on sooner. And with our mobile unit, you can deploy it very fast. We have to build these units, obviously, first. But it's a much faster solution than waiting for that 2024 date to come. And we've actually studied it and found that we can enable up to 550 megawatts of new wind generation capacity to be brought on as soon as our devices are installed. And that's kind of scalable too, right? So, you know, it's 2 trailers might enable you to have 200 megawatts of wind, but you just keep adding more as more wind developers are ready to connect to the grid. And so you see this way to incrementally manage the system in an efficient way. So this is just kind of one example of enabling renewables. Any questions on this one? Yeah.
How does this affect the line losses when you change the power factor? So I'm assuming that's gonna.
Yeah, and there's some line losses, but it's dwarfed by the amount of power you're able to push through the network as a whole, right? And all our devices are powered by the line current themselves, so they're all harvesting a little bit of power as well. But it's, you know, it's on the order of kilowatts, and you're able to increase the transfer capacity of the network by several hundred megawatts. So, you know, in the end, you're gaining, yeah.
Yeah, I mean, our inverter, the smart valve inverter technology is about 99% efficient. So in terms of losses through our devices is very, very minimal. But then your question about the power factor is great. So if we're going into capacitive mode, right, now we're decreasing the losses on the grid. So we're helping them out. If we're going to inductive mode, we're kind of pushing power away, then it will be, you know, decreasing the power factor, which will be increasing some of the losses on the line. But yeah, from our studies so far, it hasn't been a significant impact. Okay. That's a great question.
Yeah.
So in this case, you're kind of thinking about where the renewables are going to come in, and it can kind of go down different paths, and you know, so you want to send it all along your preferred path. In a case where, like, let's say you've got the curtailment situation that you're concerned with, where there's one line that's already congested or near capacity, and let's say somebody wants to build a solar project on that, then that's the only line they can connect to, and they can't do that because it's congestion, and so they'll just always be curtailed, and so they're never going to build that project. Now, can you imagine sort of deploying the solar, the renewable energy with these inverters, with these solutions, so that basically when that capacity is being delivered to the grid, it's just increasing the impedance, so it pushes energy upstream to go down the other wires, so that it can just feed in with sort of like a net neutral capacity, not changing the sort of overall congestion of the wire, and sort of enabling those solar projects to happen. Is that something that you guys have thought about?
Yeah, I think. Yeah. So, are you talking about a situation where? So let me back up. So there's kind of two situations. There's one where solar farms and wind farms can sometimes connect to a radial line, right? We call it. So there's really only one path for that power to flow to the network, right? In that instance, we can't really help anything. But what often happens is that line might connect to a larger mesh network of the rest of the grid, right? And what happens is by connecting that solar farm at that point, the radial line doesn't overload. It's something else on this network where that power eventually flows. And so there we can sort of time it and put our devices there on that network when that solar farm comes online, and it eliminates that constraint further downstream. So you kind of, it doesn't really directly affect the power flow on that interconnection line, but it
so you can't sort of simultaneously put in extra power onto a radial line and then also deflect upstream power onto different radial lines that are upstream of where you're connecting in.
I'm not entirely tracking.
Okay, yeah,
So
that's fine.
I think I understand. He's trying to say we can move one section of power to some other line to open up space for the new power generation.
Yeah. So, okay.
Exactly.
So if you have this example here, right? And so let's say you had one radial line and you're getting. Maybe I'll start off in kind of the original way I was going to answer this. And you let me know if that was going to help or not. So let's say on this line here, you have solar 1 and they come on, and you have solar 2 come on, and when solar 2 comes on this line, now we start having congestion issues on that line. So so you could put our devices, let's say over here, and that would pull solar 1's power up this way to get to this load, while solar 2 can still get out to this load. Right. So we have looked at situations like that.
Yeah, I was thinking of it as instead of pulling the solar power, into a different direction, pushing upstream power off of that line.
Oh, gotcha. Yeah. You could also, so again, doing grid topology studies, there's always, more than one way to cut that onion. But say this line's getting congested. Maybe putting some devices over here, starts pulling power away, and you could free that up. So definitely. And that's part of the reason why we have this data analytics solutioning team that's trying to figure out how can I look at these, because grids are much bigger than this. How can I look at that big grid and identify what's the optimal location for this? Sorry, go ahead. Yes.
So on your graph, the transmission graph, when you're optimizing the graph, usually which variables are you optimizing for at the same time? How many variables? Is it 1 or 2 or 3 or?
What variables are you referring to? Can you just expand on that?
So the amount of power, or the you can think of it as navigating in ways like A-star search and linear programming, where you have you're manufacturing something and you want to produce something in linear programming, and you have multiple constraints.
Right.
And so what I was saying is, what constraints do you have? Dollars as a constraint and power as a constraint? You could optimize for one variable and achieve that, but usually you're trying to balance. It would be kind of like if you had a content delivery network, and if you're just optimizing for latency, that might be great, but all of a sudden your costs go way up. So usually your customers might know the things they care about. What things are they trying to optimize? Just not saturating the line, or is it also like dollars or like, so your solution for determining how much to pull or push, does that make sense?
Yeah, that makes sense. Yeah, and I would say we do a bunch of different types of studies. You can sort of so if we do like a congestion study, we can have it so you want to deploy a certain amount of SmartWires devices in a way that results in the minimal cost of generation, right? But there's also reliability studies that we'll do where we're just focused on what's the least amount of SmartWires devices needed to resolve a single overload. We're looking at like a single overloaded line in a case. And so some of the tools that our team is developing is looking at where do you place SmartWires devices on the network in a way that uses the least amount of devices to resolve that overload. So that's typically what we're looking at. I don't know if you want to expand.
Yeah, so utilities have kind of a prescribed way that they do their transmission study. Yeah, control, that was the other one I skipped on here. Yes. I added in, I kind of anticipated in, my office mate she runs it's like, R&D, we're really smart. So my office mate runs the development of what we call our end-to-end control system. We'll kind of just skip through the whole thing. So our devices in the field communicate the smart bypass. Remember we have the smart bypass and smart valve. The smart bypass acts as the communication hub, and we have RF that goes from that device along with the mesh network with the devices around it, and they go down to the power line coordinator, which goes to the power line gateway, which goes back to the energy management system. Typically, this can be deployed in a few different flavors, but we'll kind of just go with the typical one for this discussion. So the energy management system, sometimes utilities say, hey, these are the preset, when you see this current, I want you to be in this injection mode at this percentage and, et cetera. So sometimes we just develop, controlled algorithms to have these operate based on the feedback it's getting. And so we have all of our devices, we've developed a phase lock loop, a PLL, so it gets its timing off of understanding the phase of the grid, and that's how we know when to inject, when not to inject. So all that is done in real time. So in addition to kind of being able to set predefined parameters and just have them control themselves autonomously, the energy management system can also control them to where they hit a button and it goes on, they can hit a button and it goes off, they can hit a button. So we can deploy this and configure this in several different flavors. So a little bit about the communication system. It is incredibly detailed, and we have the person who has deployed more smart meters than like anyone else. He's our head of cybersecurity for understanding to ensure that this is not unhackable because nothing's unhackable, but hard, difficult too. I mean, I know we've gone to several penetration tests so far, and so far no one's been able to get into our devices. And I'm trying to think what else I might point out. Any other questions about kind of the communication system aspect of it?
How long can you operate if you lose communications? Like, what do you do when you're in a no communication mode?
Again, configurable. The way I'll answer that question is our number one priority is to ensure that the line always stays in contact. We never want to break the line. So a lot of steps that we do when kind of something fails or something goes down is we just go back into that what we call monitoring mode to where we just have the line connected and our devices are off. It's kind of the standard anything when there's failures. Otherwise, I kind of like this question, so maybe we'll end with this. Utility business models. And how does this impact that? I mean, I think that one of the exciting things for us is, we're really a partner to utilities. We're helping, enable better services from the utilities to the ratepayers. So, it's incredibly exciting for us to work on this problem with utilities. The one thing I would highlight is that we've seen a huge uptick in Europe for us. And a lot of reason for that is in Europe, you have an enhanced rate of recovery. So again, utilities, the way that regulation has set them up to act is I put stuff in the ground, I invest capital in that, and I get a guaranteed rate of return from my ratepayers based on that capital. So I just want to spend as much capital and put as much stuff in the ground as possible. what we're seeing that change a little bit, especially it's happening more quickly in Europe, is that if I do a traditional reconductor, build a new line, I get 8% rate of return. But if I do something that is cost effective for my ratepayers, my regulator said I can get a higher rate of return. So if I do something like SmartWires, now instead of that 8%, I can get 15, whatever percent. So now I'm very much more incentivized to do something that is way more cost effective than reconducting or build a new line. But my investors aren't going to be hurt because I'm still going to get a good rate of return on that, and better than I would have the capital had I done a traditional product. And then the ratepayers are also making out because they're not having to spend these $90 billion a year on just building new lines or reconducting lines. We are seeing some talk and so hopefully some uptake soon in New York and California, I think, with enhanced rate of recoveries. But that's one mechanism that I've seen so far from a utility business model I think would be super exciting for us.
Yeah. And it's called performance-based regulation if you're interested in looking it up. The UK does it really well, and we've got a lot of work there.
So have you thought with partnering with people that are doing development to say have like a combined solution of we're going to put in a big solar farm and we're going to put in these smart wires and then we can deliver at this cost, that and then by having the smart wires in there, it allows the solar to not have to take in so much curtailment into their sort of like roll that into their cost.
Yeah, we've got a couple people focused on exactly that and talking with developers to try and walk hand in hand with the developer to the utility and say, hey, you told me it was $20 million to reconnect the lines we could get on. We studied the system and we found that this $2 million SmartWire solution could give us full deliverability. And so we're trying to figure out how to partner with those types of entities as well. Yeah.
For load flow analysis, do you have your own software or you use utilities for modeling?
Yeah, so there's all kinds of different platforms out there like PSLF, PSSE, even Power World and stuff. And so depending on where you're at in the world, everyone uses a different platform. And so we actually use those platforms, but we create tools on top of them. We come up with some optimization tools to use over the top of those platforms.
Okay, because I was thinking if there's an existing generation on the line, and any of these lines, those are pretty much built for some other power factor assumption. So when you're bringing this in, it kind of changes the main kind of assumption. So I'm just wondering if you had any experience with that, like installing these on existing generation circuits.
Yeah, so typically the utilities will share their cases with us, right? Their power flow cases that basically outline their whole transmission system. And so, we do several iterations of studies of, changing the impedance values of certain lines to simulate our devices. And so we always check and make sure we're not screwing anything up on the grid. We're not creating a whack-a-mole problem where we're pushing power somewhere else that causes a problem. So that's like a key part of our study process.
And maybe one thing that I'll add, for what we do a lot with utilities is the protection group who studies how we set all of our breakers on the system. One of the super innovative things that we did and kind of they did early on in the RPE process is whenever there's a fault on the grid, so when you want that protection study to work, we will bypass our device. So we go back into that monitoring mode, so we're not injecting any impedance. And breakers usually work on the hundreds of micro to few millisecond standpoint, and our protection system happens in the low microsecond. So we operate much quicker to get off of the grid than what the utilities infrastructure will do. So it's kind of like we don't exist. So that's one of the nice things is when you have to get the protection group involved, that's when you start adding years to your deployment. That's probably about time to wrap up, so we'll do a couple more questions, but I'm loving all the questions. So,
another question about the distribution side. So, in California right now, utilities are going through what's called the ICA, Interconnection Capacity Assessment or Analysis, to figure out how much DERs can be put on the 12 kV circuits. And they've identified some pilot areas within 2.0 version to do the whole state pretty much. But they've shown a lot of areas where there is line congestion. I am curious as to, given that you're deploying the system, basically one system at a time, there's more 12 kV circuits versus understand that there is going to be a need for this growth in DERs, to figure out how to get these lines, basically optimized to put more solar storage, EV on these circuits. Is the physical challenge of these radial lines, I don't understand exactly what that means, is that really the problem for deploying a solution like yours, or is it that the substations that are in cities are too small? And how come that's not the focus versus the transmission?
Yeah, I'll start and Brock jump in. But the main limitation on the distribution system is those 12 kV lines, they're almost never in a mesh network. So what's key about our devices is you have to have an electrically parallel path to push power onto most of the time. Now, there are some things we can potentially do in capacitive mode with our devices on the distribution system. If you're trying to pull power onto a line that's not completely overloaded, there may be an application there. But I think what we found is just the vast majority of that network, it's all radial. You don't have anywhere to push or pull power to. And what we found is, in terms of the cost of deploying some of our devices, if you're doing them up at the transmission level, you're able to push and pull a lot more power, right? If you're on a 12 kV line that serves a handful of homes, it's hard to make that cost benefit pencil if you're going to install one of our devices there. And I think, as Brock mentioned on our roadmap, that's where we want to get to eventually, is coming up with a maybe cheaper device that can work at those levels. But
Today, you think a reconductoring of those lines is probably a better solution, or load management on behind the meter is?
Yeah.
Yeah, I mean, the key point is just the radial to crystallize on what that is. So if you see this, how all of the, like, if I'm an electron here, I can flow here, 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 I can flow here, 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 I can flow here, here, here. So there's multiple parallel paths that an electron that starts here can flow down. On the distribution grid, generally, pretend this A doesn't exist, right? So if I'm an electron here, I can just go here, 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 and that's it. Technically, I could go through this load center and back up to here. But that's what we mean by radial. So radial is just kind of, it connects to this load and only goes in one direction. And a lot of times when you get down to the distribution grid, that's how it's connected. There are some, in urban areas, it's not always radial. Also, a lot of times the radial network will kind of look something, so pretend this line didn't exist and you just had a circle. Sometimes it'll be a circle, but they'll leave it not connected, so it's two radial ways. So I also looked at, could we connect that currently unconnected to try to make it a little bit more radial, or make it a little more like a mesh network. A lot of the limitation is for SmartWires to work, I need a separate path to push that electron down. And if there's only one path, I don't have that separate path. Any final questions, or? Awesome. That was super interactive, which I love in the speech. So thank you for having us, and this was great.